Uh, Today is mostly the same learning goal as the Daily Challenge 9.1, which is kind of refining our intuition about limits from the last couple of meetings. There's only two major topics in this chapter, which are limits and then continuity. I was originally going to just do continuity today and then spend a long time solving a bunch of problems, but I think it probably makes more sense to break it up. So since we've discussed limits, we can just solve a bunch of problems on those today, and then possibly do continuity and then solve a bunch of problems on that afterwards, rather than kind of bunching them together. But okay, a review, which is probably very familiar since you've just read through 9.1. So the whole raison d'etre of the last couple of meetings, the reason for the existence of those meetings was to define rigorously what we mean by this word approaching. So you'll notice in those meetings we always defined this entire collection of symbols appearing together. Limit as x approaches a of f of x equals L. So you should think of this as just, this is an entire kind of Boolean statement. This entire thing, it looks like an equation, it's not an equation. You could think of this as a dummy variable that just says derp. The derp can evaluate to true or false, but that variable derp really just stands for this entire sentence, that for any epsilon greater than 0, there exists some delta greater than 0, so that whenever 0 is less than the norm of x minus a is less than delta, then the norm of f of x minus L is less than epsilon. So this is just a sentence which can be true or false, and that's why this thing is similar to a Boolean, which is short for that sentence, although you just replace a and L in the second sentence. So it looks like it's an equation between two objects. If we wanted to make this an equation between an object called this limit, we would have to make a separate definition where the quotes would just be around this left-hand side of the limit. And if we want to make that definition, which we will, but we haven't yet, you need to justify that this is actually an equation between two numbers, which means that only one number satisfies this property. Because if we define this in such a way where we could have two different numbers that satisfied the definition, then we wouldn't be able to say, this defines a number. So you'll prove that uniqueness property in 9.1, and then we'll be able to do that other definition. Okay, so this is what we discussed in the last couple of meetings. The picture for this, which, I mean, I've emphasized a couple times, but when you do mathematics, you really have to think of it as doing two different things. You have an exploration phase where you can think about pictures and non-rigorous stuff to get the idea, but then you have to banish the pictures to write a rigorous proof. So in the first part, the exploration, you can think of pictures like this, where here's some curve, y equals f of x. They've emphasized the fact that the value at the point doesn't matter. That's encoded by this 0 is less than.
Give me a sec. People are talking to me. What? Sorry about that again.
No problem. Where was I? Here, yes. Right, so here's the picture corresponding to that definition. There's a hole in the function at the point, which just emphasizes that what happens at the value doesn't matter. That's this 0 is less than on the bottom. And then the idea is that here the limit does exist the way that it's drawn, and the reason it does exist is because for any epsilon, which is shown here as the pink bars around L, for any such epsilon, you can find a little interval from x0 minus delta to x0 plus delta, so that everything in that interval gets mapped into the pink bars. Right, so that's the definition that we saw. Some things, this is from Spivak, which you'll read at the end of this week of challenges, but just some ideas for when limits do and do not exist. In the first row, here are three functions where the limit does exist. The limit is equal to L at A. So if the curve looks smooth, it is indeed true that the limit exists at A. If the curve is smooth, but these arrows mean that it gets closer and closer to that point, but there's a hole there. If there's a hole, but it's otherwise smooth, the limit does exist. If they get closer and closer to some point which is removed, defined kind of the wrong way, as in that point is displaced from where the other kind of endpoints make it look like it should be, the limit still does exist. So in the top three, the limit all does exist at A. In the bottom three, the limits do not exist. So the reason it does not exist on the left is because we approach different values from the left and right. So you could define left and right limits which do exist, but the ordinary limit does not exist. In the second one here, the limit looks like it exists from the left. From the right, it oscillates wildly, so it never settles down and approaches one particular number, like L. And in this one, the reason the limit does not exist is because the definition was that the limit is equal to this value L. So here the limit does exist, it just happens not to be equal to L. So here the function approaches a different number. So this just captures some of the intuition. So the reason we're defining limits is to characterize kind of what sort of these scenarios is happening when we study our functions. Back to here. No. Good, so I want this one. Good. So last comment, it may seem like a jump in abstraction from what we're doing, so just to justify why this is an interesting thing to do. Because before I've said words like this thing, this limit as n goes to infinity of some expression, like 1 plus 1 over n to the n equals e. And I've kind of said this and waved my hands, but I mean, as far as our goal of developing everything very carefully from one definition at a time, building it up logically, as far as that presentation, this was officially meaningless because I haven't told you what that meant at the time. So I did the same thing in defining pi, did this with defining e, and so forth. But now it's actually a serious definition. This thing in quotes, which I said before, now you can translate into serious mathematics. We might not be able to prove it yet, but we know what this statement means. It's there exists a number e, which is the value of the limit, such that for all epsilon greater than 0, there is some n. So this is the different definition for a limit at infinity, right? So now you just say there's some positive number n, so that whenever I go larger than n, lowercase n is bigger than capital N, then this expression will be within tolerance epsilon of e. So this is very important as you go on in mathematics. This is in number theory. You use this to define asymptotics of the prime number theorem, the density of the primes. This is how we define the derivative and the integral, which are the fundamental objects in calculus. This limiting procedure is how one defines differential equations, which are basically all that any practicing scientist or engineer ever does, is choose differential equations that capture some aspect of real life and then solve them. And all the differential equation is some relationship between different limiting procedures. So everything builds out of this. Good. Okay. So that's the review of everything we did before break. So thoughts or questions on what we have said so far?
I do have a question about the examples from the Spivak book.
Ah, good. That's here.
The fourth one, if you're reading it like a book. I do not understand why a limit does not exist for that, actually.
Okay, so here, let me zoom in a little bit. The point that he's making is that this arrow, it approaches a slightly different number. You see what I'm saying?
Right, I totally forgot about that.
Yeah, so if you're thinking about the left and right limits, those exist, but they're different numbers. It's kind of like the, remember the function you defined 2 meetings ago where you said it equals 1 if x is negative and it jumps up to 2 if x is positive? That thing?
Yeah.
Yeah, so that's the same idea as here. The limit doesn't exist for that one because it has different values from the left and right.
Okay. Now I see. Cool.
Good, good. Other thoughts on this?
What is happening? Someone else is calling me. Why does this happen so often?
I will be here.
Yep, I'm still here.
Oh, you're not going to take that?
What? No.
Oh, okay.
They want to play Fortnite.
Lol. Good, okay. Let's look at some proofs. So I will do 3 proofs that are basically stuff that we've seen before, just to get us warmed up, and then I'll ask you to help work through another one. So the easiest time that you can prove that a limit exists is if a function is constant, right? So if you pick some number c, maybe 1 for instance, and define f of x equals c. So that's just a horizontal line. For instance, y equals 1. It's the same everywhere. You would certainly expect that limits exist there because as you get closer and closer to any input, the output is always 1. So it certainly gets close to 1 if c equals to 1, or c more generally. So the proposition is if c is real and f of x equals c, then for any other number a, the limit as x approaches a of f of x equals c. Here's the proof. It's very simple. You always need to show that given any epsilon you can find a delta. So we start by saying let epsilon greater than 0 be given. And now you can let delta be any number whatsoever. If you want to be specific, you could choose delta equals epsilon if you want. It doesn't matter. The reason it doesn't matter is that we need to show that if x is is within a distance delta of a, but not equal to a, then f of x is within a distance epsilon of c. That's what we need to prove. But we don't even need to use this assumption. It is automatically true that this absolute value on the left, f of x minus c, will be less than epsilon, because f of x equals c for all values of x. It's a constant function. So c minus c is always 0, and therefore the absolute value of f of x minus c is always 0 for any value of x. So just a quick concept question. How do we know that if the left side of this inequality is 0, if f of x minus c is 0, how do we know 0 is less than epsilon? What if epsilon's like minus 1? It's not true that 0 is less than minus 1.
It doesn't seem that epsilon can be minus 1.
Right. Why is it not the case that epsilon could be minus 1?
Since we previously defined epsilon to be greater than 0.
Good. Yes. So we always choose positive distances epsilon. So the fact that the left side is 0 means it's automatically less than epsilon, since 0 is smaller than any positive number. Good. My former student, Colin, who I've mentioned a few times, he likes writing proofs that are trolly and kind of make the reader say what the fuck. So he would often begin proofs by saying, let epsilon be less than 0. And then he would write the rest of the proof just flipping the sign everywhere, because everyone who does calculus is so used to reading proofs that begin let epsilon greater than 0 that when you see let epsilon be less than 0, it gives you like a head trip. I find this very funny. Okay. Alright, so constant functions, yeah, that's boring. How about a non-horizontal line? Any line. So there's a lot of words here. I will ask you to read aloud the proposition so that I don't have to say all the words.
Alright, here we go. Proposition. Let M and B be elements of the... Wait, I believe that's a rational set.
R for reals.
Suffering. With M does not equal 0, and let f of x equal mx plus b. Then for any A that is an element of the real set, we have the limit as x... Okay. I'm trying to remember how you worded this. The limit of f of x as x approaches A of, equals m times a plus b. That couldn't be worded very good.
Yeah, that's fine. Yeah. So one question, why did I say the slope is non-zero, m not equal to 0? I claim that we've already handled that case, so I don't need to worry about m not equal to 0. So why do we not need to handle that case?
Thinking. Because if the slope is 0, then... let me try and think about this.
So if the slope is 0, what kind of line is it? What does it look like?
It's a flat line.
Yeah, it's a horizontal line, y equals b. And what did we prove on the previous slide? So it looks like this is a horizontal line, right? This is a flat line as well, just with a different letter. So on this slide we already proved that the limit exists for every horizontal line, a flat line, equal to some constant.
Oh my god, that took me way too long to think about.
That's fine. It's just we're building it up step by step. So we did the easiest case first. We handled all the flat lines. Now we're going to handle the slanted lines. That's why I can say the slope is non-zero, because I don't have to prove the case when m equals 0 because we already proved it back here. Good. Okay. So as you read, we're going to show that the limit as x approaches a of this line, mx plus b, is ma plus b, which is what you'd expect. I mean, it's very tempting to think that the limit is the same as just plugging in the value a for x. But as you've seen for other functions like stars over Babylon or the Dirichlet function. That's often not true, so you have to break yourself of that habit. It happens to be true in this case. Okay, how do we prove it? Well, as usual, unless you're con, you say let epsilon greater than 0 be given. So you think of it as a game, someone hands you an epsilon, you have to find a delta. And I won't go through the explanation of why we picked this one, because we've actually done this already. You choose delta to be epsilon divided by the absolute value of m. No worries about dividing by 0 here, because we've assumed m is not 0. Now we just have to show this works. By works, I mean it satisfies the definition. So if the absolute value of x minus a is between 0 and delta, which means x is within distance delta of a, but not equal to a, since delta is equal to this, I'm just plugging in delta on the right side. Plugging in delta on the right side would give us absolute value of x minus a is less than epsilon over the absolute value of m. Then you can multiply both sides by the absolute value of m. So if I do that, on the right side you clear the denominator. There's no absolute value of m downstairs. On the left side, so I showed you this property last time, that the product of two absolute values, the absolute value of m times the absolute value of x minus a, can be simplified. You can move the m inside. Right? So in that step I've just moved that inside. So now I'll ask you about this last step. So we've proven this just by multiplying through by the denominator. How did I go from this step, absolute value of mx minus ma is less than epsilon, to this step, absolute value of mx plus b minus ma plus b is less than epsilon?
Could you perhaps zoom out a little bit?
Oh, yeah, sorry.
It would seem that this is reasonable by the I'm trying to remember its name. Actually, this is I can't think right now.
That's okay, even if you don't know a name for it. What algebraic step did I do to go from here to here? What's different inside the absolute values?
We just added b.
Added b and subtracted b, right?
Oh.
Right.
Yeah, I did see that at first. Now I understand.
Good. So they're the same because I've just added 0. I added 0 in a very clever form. 0 happens to be equal to b minus b. So I've added b minus b, put one of them, put the first b here, put the minus b here. You just have to remember to distribute the minus. Good. So this should certainly be true because I'm allowed to add 0 to anything. Okay, but that proves the claim. Since all we have to do, I'm just going to go back to the definition quickly. If you're ever asked to prove a statement that involves this collection of symbols, all you have to do is show that given any epsilon, you can find a delta so that this thing is true. So in particular, after assuming the first part, I have to prove this thing is true. F of x minus L is less than epsilon. But that's what we've done here because f of x equals mx plus b. So the first part here, this is f of x, and this is L. This L is the value of the limit that we're trying to prove it approaches. So this is absolute value of f of x minus L, and it's less than epsilon. So we have proven exactly the statement which appears in the definition, which means that, oh, I forgot, there's a typo here. This should be ma plus b. I forgot the plus b. I will go back and actually fix that right away. But, yeah, my computer's being too slow because I have too many things running. Okay, maybe that will not work as expected, but modulo the lack of the plus b at the end. Thoughts on this proof? Or are there steps that are unclear?
I do not believe I am totally understanding how we went from the final centered equation, inequality, to our final line.
Ah, okay. So let me... this has finally appeared. See, I'd like to be able to write math in real time so that you can see what I'm doing rather than highlighting, since I do not have the drawing tablet, but it's too slow. Okay, let's get to where we were. Okay, linear functions. Okay, so how did we go from this inequality to the final line that the limit as x approaches a of f of x equals ma plus b? So the reason for that is that maybe I'll put one more step of explanation in and also correct this. So I'll put a comma. I don't know if there'll be enough room for this actually. This is f of x minus L less than epsilon. And I'll align this and less than epsilon. Comma, where in the last step we have used that f of x equals mx plus b and L equals ma plus b. But this is the definition of the limit, so now it's going to take 10 years to render. Okay, so here, now there's two lines. This was the last line before, mx plus b minus ma plus b. So now I've just done a substitution. In the last step we've used f of x equals mx plus b, so I've taken the first set of parentheses and plugged in f of x. In the second step we've used that L, which is the value that we're trying to show the limit has, L equals ma plus b, and I put that in for the second term. So this is just a substitution. So we've shown that the absolute value of f of x minus L is less than epsilon, assuming that 0 is less than the absolute value of x minus a is less than delta. So the thing that we've proven is that whenever 0 is less than absolute value of x minus a is less than delta, it automatically holds that the absolute value of f of x minus L is less than epsilon. But that long sentence that I just said is exactly the sentence which the limit existing is shorthand for, right? So whenever you claim you have proven this sentence or this symbol, limit x approaches a of f of x equals L, that's really just shorthand for this sentence. So all I'm saying in this last step is we have now proven that that long sentence holds, that this implies this, and therefore the limit exists because this last expression is just shorthand for that sentence. Does that answer the question, or is it still murky?
Yes, it does. That makes much more sense now.
Okay, good. Yeah, it's good to keep in mind whenever you're asked to prove something that has a conclusion that says a limit exists, your brain should just unpack that. It means you have to show that absolute value of f of x minus that number L is less than epsilon. So once you've done that, it's proven. Good, okay, so we did something similar to this last time. Let's just review the idea. Here, in the previous example with a linear function, choosing delta was very easy. You could pick delta in one step. You just divide by the slope. When the function is more complicated, like a quadratic, you often need to make a starting assumption. So what do I mean by that? Our proposition now will be let f of x be x squared, the quadratic, and we want to show a specific value, x equals 2, rather than just any number a. We're going to pick a specific number. The limit as x approaches 2 of x squared equals 4. So I'm not going to jump right ahead to the proof. I'll show you how the exploration works. This is how I think when I try to prove that a limit exists. So I immediately unpack this sentence, right? This limit existing sentence, all this means is that we can make the absolute value of f of x minus 4, which is the absolute value of x squared minus 4, small, where small means less than epsilon. So my brain immediately replaces this by the definition, we can make this thing less than epsilon. How do I make that thing less than epsilon? Well, first you do some playing around. You do some exploration. Since this is a difference of squares, you might think to factor. So if we factor the absolute value of x squared minus 4 into two pieces, then that helps a little bit, since the first piece is something we have under control, since we're always allowed to make that smaller than delta. That's how the limit works. You're handed the epsilon for the output, you're allowed to choose the delta, which is the absolute value of x minus 2, that gives the input tolerance. We know how to use that term. The second term is harder to deal with. We don't know anything right now about the absolute value of x plus 2. We only know that we can make x close to 2. So you first make a starting assumption. Since eventually we're going to make x close to 2, you might as well start by assuming that x is reasonably close to 2, say it's within a distance 1 of the value 2. So we start by imposing absolute value of x minus 2 is less than 1. Then I just translate that into this chain of inequalities. If x is within distance 1 of the number 2, then it's certainly between 1 and 3, because those are 2 minus 1 and 2 plus 1. So if x is between 1 and 3, the biggest that the absolute value of x plus 2 could possibly be is 5, since the biggest value of this thing occurs when x is 3. So it's upper bounded by 3 plus 2, which is 5. So under that assumption, we can replace the right-hand side of this factored expression with an upper bound of 5 for the x plus 2 term. This is very common in showing that limits exist, is that you need to think of some idea to bound a term whose behavior you don't understand. So here we bounded x plus 2 by 5 and just replace that. So this is a key step, and the next example I'll ask you to do one that's somewhat more complicated than this. So try to formulate a question, if you can, about what we've done here.
I don't exactly have any questions outside of asking you to go over that again because I don't understand it.
Okay. Yeah, how to start. Okay, yeah, let me do the big picture from the beginning. So I'll run through what my brain does when I see this. My brain says, I would like to prove the limit as x approaches 2 of x squared equals 4. So this is a Python variable. This is like some expression derp, which I've defined previously. So my brain automatically retrieves the definition of this compact statement. So my brain retrieves that, and I go back to the previous slide where it retrieves it from. Aha, anytime I write this, I really mean this. So I'm just going to put in 2 and x squared and 4. So the thing I'm being asked to prove is that if you give me any epsilon, I can find a delta, so that when the absolute value of x minus 2, that's a, absolute value of x minus 2 lies between 0 and delta, then the absolute value of x squared minus 4 is less than epsilon. That's the kicker, that last thing. The implies means I have to prove that this thing is true. So my brain immediately focuses on this part of the sentence. I need to prove this thing is true. So that's what I wrote in the next step. The f of x minus L, that's this part. This is the f of x minus L, because L is 4. So I focused on that part, which, plugging in the value of f of x, which is x squared, this is the f of x minus L. So my brain's like, okay, you need to prove that this thing can be bounded. You can make it smaller than epsilon. So that's the definition of the limit. So the first thing, I guess this is many steps. I should have broken this up into steps. The first step my brain does is retrieve the definition and then identify the goal that we want to make this thing small. So is that first step clear, or should we discuss that more?
I still do not believe I'm understanding our goal is to make insert equation small.
Okay, so is it clear then the first step, retrieving from the definition, is it clear that what we want to prove, this statement that I've highlighted, that is equivalent to saying for every epsilon greater than 0, I can find a delta greater than 0, so that when absolute value of x minus 2 is between 0 and delta, the absolute value of x squared minus 4 is less than epsilon, where the emphasis is on the last part. So is the step of replacing the highlighted expression by that long sentence clear?
Yes.
Okay, so if, actually can I use, maybe this would be, it's too slow. I was going to try to type LaTeX in Math with Slack, but I think it's being too slow. Okay, so once you've replaced this by that expression, then we realize, well, to write this proof, I'm kind of thinking ahead, because we're still in the exploration. But when I think ahead, I say, well, the way this proof is going to look is I'm going to start by saying, let epsilon greater than 0 be given. So you hand me an epsilon. Then my job is going to be to cook up a delta. So I'm planning ahead, because I'm not writing that proof yet, but I'm trying to think about what is that delta supposed to do. What that delta is supposed to do is have the property that when x is within distance delta of a, then f of x is within distance epsilon of L. So in thinking ahead, I'm trying to create a strategy for arguing that the absolute value of f of x minus L will be smaller than epsilon. Because that's what I need to prove. The absolute value of f of x minus L is smaller than epsilon once I've made these assumptions. So we have to kind of be strategic and think a couple steps ahead, because we know in this proof we're going to have to make this smaller than epsilon. So you start brainstorming, how do I make the thing on the left side small? Because I want to make it smaller than whatever epsilon you've handed me. So then in going from that, this big sentence to the next step of that exploration, all I've done is plug in those two values of f of x and L. Right, so f of x is x squared, and L is 4. So this is the thing which at the end of the day I need to convince you, or convince the reader, is smaller than whatever epsilon you've handed me. All right, does that make it clearer or worse? It's okay if it's worse. Sometimes I make things worse when I talk more.
I think I'm understanding it slightly better.
Okay. Do you want to try?
I was getting really hooked up on how absolute value of f of x minus 4 equal, like making that equation small.
Oh, okay. I mean this expression. Yeah, sorry.
Yeah.
Right.
I was like, so I have no idea. I got hooked up on that so bad because I was like, it's obvious they're equal. What?
Yes, yes. I've done a bad thing. You shouldn't write this way in proofs, but I'm being sloppy in the exploration. I mean,
okay,
this whole expression, which happens to be equal to this other expression, they both need to be small because they're the same thing. But I really mean we're going to make this side small.
Okay.
Apologies, that's my
Now
slop.
to the next step.
Good. Okay. So the factoring. So you haven't proven this yet. I've actually proven it for you in 9.2. But this thing that if you factor this inside the absolute value, then you can split it into two absolute values. So I'll prove that. I have proven that for you. You'll read it tomorrow or Tuesday or whatever. So are you okay with this factoring and then splitting it into two pieces?
Yes.
Okay. Now, this is the tricky part, because when you're looking at this, if you don't have that definition firmly in mind, it might not be clear which of these is easier to bound than the other. So again, if we go back to the definition, we're trying to prove this limit exists, which means the absolute, here a is 2, right? So this number is a. So we're allowed to assume in our proof that 0 is less than the absolute value of x minus 2, because a is 2, is less than delta. And remember, we get to pick delta. So we have the absolute value of x minus 2 completely under control. We can make that as small as we want because we get to pick delta. If we want to make it less than a million, just choose delta as 1, or less than 1 millionth, just choose delta to be a millionth, and then the absolute value of x minus 2 will be less than a millionth. If you need it smaller, if you need it less than a billionth, we just pick delta to be a billionth. So we can make absolute value of x minus 2 as small as we want. That's part of the game. So That's why I say here that we have the first factor, absolute value of x minus 2, under control, because we can make that smaller than whatever delta we want. So, I mean, this thing is not really a problem to worry about. It was kind of hand-wavy, but is that clear? Or sensible, I should say. Clear is perhaps too strong a word.
Yes.
Okay. Right, but in that definition, it didn't say anything about you're allowed to pick another number, a delta 2, that will make the absolute value of x plus a small. That's not true. We're not allowed to say anything about x plus a. We're only allowed to make x minus a small, right? So that's why I say this thing is tricky. And then this is how we solve the trick. We convert the power we have over this first term, which is the power to make x close to 2. We're going to spend some of that to bound on this guy, this second factor. So what we do is say, well, we have the power to make x as close to 2 as we like, and maybe later we're going to make it even closer than 1 distance away from 2. Maybe we will, maybe we won't, I don't know. But for now, we're at least going to exercise our power to make it a distance 1 from 2 at most. If that's true, if we've guaranteed that x is within distance 1 of 2, then it lies in this range. Distance 1 of 2 means between 1 and 3. If it's in this range, now that other factor, which before we knew nothing about, now we have an upper bound for it. Because the biggest that x plus 2 absolute value can be, if x is between 1 and 3, is 5. So here the strategy is very important. We know a lot about this, we know nothing about this, so we spend some of our freedom to restrict this guy in order to get a handle on the second guy. We say x is in this range, which gives us an upper bound on the second factor. Okay, questions on that part?
I believe I'm understanding that part.
Good, okay. So then all I've done here is replace the second factor by 5. Okay, so this I think is enough to stop the exploration, because now we can almost immediately see how to do the rest of the proof, because we want this to be less than epsilon, and this thing we can make less than delta. So I think if we pick delta to be at most epsilon over 5, then the 5's will cancel, and the left side will be less than epsilon. So whenever you get this sort of relationship between the thing you want to be small is less than a constant factor times the thing you can make small, you're basically done. But I'm going to write that out more carefully on the next slide. So here's the full proof. Amusingly, the full proof is shorter than the exploration, as is often the case. So same proposition. F is x squared, limit as x goes to 2 of x squared is 4. Here's what we do. Let epsilon greater than 0 be given. You hand me an epsilon. I choose delta to be the smaller of 1 and epsilon over 5. The reason we need to pick the smaller of these two is that we paid the price for making this assumption in the first step. We assumed x is within distance 1 of 2, which means delta is at most 1. And then later we also want to say, yeah, well, we also want delta to be less than epsilon over 5. We want both of those things. So we want delta to be smaller than 1 and delta to be smaller than epsilon over 5. And the way to do that is say, well, delta is going to be the minimum of those two. If epsilon over 5 is bigger than 1, then we pick 1, and otherwise we pick epsilon over 5. So that's the choice. Then you just have to show that it works. So the definition of a limit says that if, I should have put a 0 here, if 0 is less than the absolute value of x minus 2 is less than delta, then this thing, as we argued on the previous slide, absolute value of x plus 2 is at most 5, because x can be at most 3. So this thing's at most 5, and therefore the product, absolute value of x minus 2 times absolute value of x plus 2, is at most 5 times the value of delta that we picked. Delta is definitely smaller than epsilon over 5. So if delta is smaller than epsilon over 5, 5 delta is certainly smaller than epsilon. And then that's it. Then we're done. Because this is f of x minus L, this is epsilon, So that's the definition of a limit. When you've shown that this thing is less than epsilon, you've completed the proof. Okay, lots of moving pieces there. What do you think? Too overwhelmed, perhaps?
It would seem that, okay, was our entire goal here proving that a limit exists?
Yeah, so...
Okay, that makes much more sense.
Yeah, so proposition is like a theorem. We're trying to prove this statement, right?
Okay, yeah. So yes, oh god, that was my phone.
Did you just drop your phone?
It fell in my pocket. It's all good. Yep.
Don't
I am understanding what is going on. Yeah, understanding is way too overkill for this situation. I have an idea what's going on.
Good, okay. We will improve that to understanding with time. Alright, let's do a more fun one. So this is the same structure. We're trying to prove that this limit exists. And as an aside, there's going to be basically only two kinds of problems in this unit. Proving a limit exists, where you have to basically pick a delta, give it an epsilon. A second kind of problem is you assume a limit exists and prove something else. So in that case, you have to use the epsilon delta definition, but you don't have to explicitly pick an epsilon. So this is the first type. We're proving a limit exists. So now it's an x cubed, and we want to prove the limit as x goes to 2 of x cubed equals 8. Alright, so this is very similar to the last one. I actually copy-pasted the first part of the exploration. Same thing. This is f of x minus L. So that's the thing in the definition. We have to prove absolute value of f of x minus L is less than epsilon, smaller than epsilon. So our goal is to make this thing small. So we'll try to repeat what we did in the square case, and I'll let you tell me what should go in the question marks. If we try to factor out the thing we have control over, which is x minus 2, out of this cubic, what goes in the question marks?
So can we, it would seem that we might be able to apply the difference of two cubes here.
Yes.
Wait, no, is that the right word?
Yeah, difference of cubes, because x cubed is cubed and 8 is
I don't know why I said two cubes.
So
but,
what?
Yeah,
so
thing.
Do you remember difference of cubes? What goes in the second factor if we're using difference of cubes? Go down here and I can plug it in as you tell me.
Trying to find, there it is. So that would be breaking into x minus 2 times, well, the absolute value of x minus 2 times, deep thinking, x squared plus 2x plus 4.
Good. X squared plus 2s plus 4, because it's let's see, a cubed minus b cubed, so we have an a squared plus an ab plus a b squared. Yeah, exactly. So x squared plus 2x plus 4 is right. Okay, so now we have the same problem as before. We're trying to prove that this product is smaller than epsilon. We can make the first piece small. You can make x minus 2 as small as you'd like. We don't know anything about this quadratic a priori at the beginning. We don't know anything about it. So let's do the same trick. What do you think, what starting assumption should we make in order to get a handle on the second factor?
can we do a similar thing to last time, and basically in the restricting of the, yeah, if restricting is the right word.
Yeah, that's fine.
In the restricting of the first factor, like inadvertently restrict possible values of x, and possible results of the second factor.
Yeah, that sounds good. So we'll, like you said, restrict the first factor. We'll restrict the first factor. How much do you want to restrict it? So we'll say x minus 2 is less than how much?
I mean, I guess 1 will work again.
Yeah, that's fine.
Things that are absolutely necessary for whatever reason.
Sounds good. So if x minus 2 absolute value is less than 1, let's see, that's the same thing. X lies between 1 and 3. So now, in this case, if x lies between 1 and 3, what's the upper bound for that second factor, that messy quadratic?
I'm assuming that I'm just being asked to do math here, so the upper bound of this second factor would be 19.
Good, yes.
Cool.
Because let's see, 3 squared is 9, plus 6 is 15, plus 4 is 19. So, and this, the second factor is upper, it's hard to type when there's a long lag, upper bounded by 19. Good. Okay, so that means begin a line. Absolute value x cubed minus 8 is less than 19 absolute value of x minus 2, which means now we're kind of closing in on the proof. So we've restricted our delta to be at most 1, and now we see there's a relationship between the thing we would like to make smaller than epsilon, which is this x cubed minus 8. That thing is upper bounded by 19, which you just told me, 19 times the absolute value of x minus 2. So this is what we got so far. But now we're basically done. We want to make the left side smaller than epsilon. We can make this part of the right side, absolute value of x minus 2, as small as we'd like. So if we want the whole thing to be less than epsilon, you might as well make this right factor smaller than epsilon over 19. So if this is smaller than epsilon over 19, then the left side is going to be smaller than epsilon. Because 19 times epsilon over 19 is epsilon. So then we're basically done. Let's just write it out slightly more neatly. So same thing, proposition. Let f of x equals x cubed. The limit of, as x approaches 2 of x cubed is 8. And how does the proof go? Same thing. Let epsilon greater than 0 be given. You hand me an epsilon, I have to tell you how to get a delta. Choose delta to be the minimum of 1 and epsilon over 19. So again, why the minimum? Because we restricted at the beginning delta to be at most 1 to get some control over the second factor. Once we did that, we decided we also wanted it to be at most epsilon over 19 to get rid of that multiplicative factor of 19. So we want delta to be smaller than both of these. And to do that, you take the minimum. Good. Now we just have to show this satisfies the definition. So the definition is that if the absolute value of x minus 2 is less than delta, technically also greater than 0, if x minus 2 is within, is absolute value is less than delta, then this should be cubed. Absolute value of x cubed minus 8, same factorization as before. This thing is at most 19. This thing is at most delta. So the product is at most 19 delta. Delta is at most epsilon over 19. So 19 delta is at most epsilon. So modulo the typos, we've shown that the thing f of x minus L in absolute value, that thing is less than epsilon, which is the definition of the limit. So we've shown that the long sentence which this highlighted expression unpacks into is true, and then we're done.
I accidentally noticed this last time, but what if the value for delta is epsilon over 19 and multiplying by 19, so epsilon is less than, Yeah, epsilon is less than epsilon. It's
Yes. Sorry, there's another typo. This should be less than or equal to. Yeah, because I agree. If the value of delta is exactly epsilon over 19, then these two will be equal. So the last one will be an equality. So I should have written less than equal here. The reason that doesn't kill us is because we have a less than here. So if you have a chain, you see what I mean? This is
nice.
Yeah, so as long as you make sure you have at least one less than in your chain, it doesn't matter if the last one is an equal, because it's still less than.
Okay. Yeah.
Good.
Cool.
Okay, other thoughts on this procedure?
I'm understanding it better now.
Good, okay. So at this point you might think, is this what calculus is? You just go through and pick more and more complicated functions and go through wildly difficult methods of choosing deltas given epsilons? And the answer is no. So you do a few examples to get the idea. I'll ask you to do one more in the consolidation document where you do to the fourth power. You can basically see how that'll go. You have a linear factor. This will then be a cubic. You get an upper bound. You do the same thing. Fine. So eventually you get bored of these and you think, it's kind of like writing a Python program to compute the first 10 primes. Then you write a program that computes the first 20 primes. Then you write a different function that does the first 30 primes. At some point you're like, this is getting ridiculous. Why do I keep doing the same thing over and over? Why don't I just write one function once and for all that takes an input n and it computes the first n primes? Then I'm done. I've solved all of those cases. I don't have to do casework anymore. So eventually we're going to do that with these limits. We've done constant functions, we've done lines, we've done quadratics, parabolas, we've done cubics, and at the end of maybe next session we'll be able to just write a general proof that any polynomial will have this property, that the limit as x approaches whatever number you like a of that polynomial is exactly what you would get by plugging in a to the polynomial. So I'll write one general proof and then we're done. We don't need to handle these special cases anymore. And that's very nice because you don't want to always have to be going through this complicated procedure. But it's good to see the complicated procedure a couple times because if you don't see how painful it is, then you don't understand why you would want to generalize it and solve all of them at once. So that's the goal. Does that make sense? Questions on the goal?
No questions about the problem specifically, but two thoughts. Am I going to be doing a lot of... Actually, no, you don't do a lot of proofs in high school calculus. Never mind.
Yeah, you'll do effectively none, which is very sad to me.
Okay. Cool. I mean, what? No. Why did I say cool? I was like, oh, that's the cool, the American education system. I can speak.
Yeah, your high school calc class, probably even in the cyber school, will be what I like to call monkey see, monkey do calculus. And by that I mean the teacher will stand in front of you and tell you something like, well, this is something we'll do later. He'll write down a function like f of x, or maybe he'll show you a video where he writes it down because it's cyber school. But you see a video where the teacher writes down f of x equals x cubed, and he'll say there's a thing called a derivative. The derivative of x cubed is 3x squared. Here's how I got that. I took the exponent and I pulled it down and subtracted 1. So x cubed goes to 3x squared. Similarly, the derivative of x to the fourth is 4x cubed. The derivative of x to the fifth is 5x to the fourth. Make sense? Good. Now here's a worksheet. Do problems 1 through 20 odd, and they will all be different functions like f of x equals x plus x squared, f of x equals 3x cubed, and you will do the same thing over and over where you mindlessly pull down this exponent and then subtract 1 and write the answer and put a circle around it, and you'll hand it in and you'll get a 100 and you'll feel good about yourself. But after that procedure, you will have no fucking clue why you would pull down an exponent and then subtract 1, or what that is doing, or what any of it means. And your entire life will be a lie. So that's what I'm trying to avoid here, because if you prove everything, including when we get to the derivatives, why you should pull down an exponent and subtract 1, which has to do with the appropriate limiting procedure, if you prove all of that, then when someone comes to you and asks, why is it that the derivative of x cubed is 3x squared, then you will be prepared to answer. You'll say, it's quite easy. You use the binomial theorem, you cancel out the leading factor, and then you just write it down, and it's 3x squared, and you can show them. That's the goal of what we do. That's why I call these on YouTube Calculus Done Right, because I'd like you to understand why you are doing what you are doing, and not just monkey see, monkey do. I got more emotional in the middle of that sentence than I intended.
I loved how you progressively got louder. That was awesome.
I apologize for my anger, but it makes me quite upset.
Please tell me you're recording.
I am.
I totally forgot what my second thought was to say there. Anyways.
Crap. Well, was it also related to...
Oh, wait. Yeah. But no, not really related at all. I was very interested in, similar to how we got the angle addition formulas for sine, cos, and tan, I would be super interested in understanding how the quadratic formula works at all.
Like how to derive it?
Yeah.
Good. I will... Yeah, Corbin wrote a proof. I will do one better. I will write a proof of the quadratic formula. Did you ever wonder... You have a formula that will solve any quadratic. Did you ever wonder, is there a formula which can solve a general cubic third-order equation?
I never thought about that, but I was going to say, as soon as she put up the quadratic formula, I was like, where did this come from?
That's monkey see, monkey do in action. You write it down, you use it, you have no idea why it's true. Yeah, okay.
It's amusing. Anyways, do you hear loud car noises?
I hear like a vague hum in the background, like an engine, but that's it.
Okay, yeah, that's them watching movies. I don't even know. Anyways.
Good. So you're saying if I make a video or write up something about the quadratic formula and possibly the cubic formula, that would be interesting?
Yes.
Okay, good. I will do that either tonight or tomorrow. I think that's very useful. Good. Okay, let's do... Okay, yeah, so... well, before I go on, any other questions that were prompted by those first two thoughts?
Those are the only two questions/thoughts I had.
Cool.
I was keeping track of them once, even though I had no paper, strangely enough.
Your memory is good. I would have felt very bad if my rant got rid of your second thought. Okay, so... Alright, so I've convinced you that maybe we don't need to do more examples of explicitly picking deltas, because eventually we'll have a procedure that does it for us. So let's do a different type of problem. So I mentioned there's basically two flavors. You prove a limit exists, or you assume a limit exists and then use it to get something. This is the second one. And if you Google Terry Tao and epsilon of room, I think I've told you about Terry Tao before, he has this collection of, he calls it a trick wiki. It's a collection of math tricks, which when proving something hard, often there's a nice trick which makes the thing much easier. And this is one of his tricks, called giving yourself an epsilon of room. If you want to prove something that doesn't really involve epsilons anywhere, it seems like it's just a strict result, it often helps to try to convert the problem into a related one where you have a little wiggle room, an epsilon of room. And...
Do you mind if I pause for a second? They keep calling me from Fortnite. Why? Now they're calling like 17 people in a DM somehow.
Jesus, okay.
I need to text yell at them quick.
Text yell. Is this over here?
Okay, that is much better.
Good.
Anyways, I'm sorry about that again.
No problem.
The almost entirety of that spiel was me trying to get your attention and realizing I was muted.
Oh, I didn't... I apologize. So you probably thought I was talking over you. I did not hear anything.
I was just being dumb.
Alas. Okay, yeah, well, it wasn't that important.
I heard up to the Terry Tao part.
Okay, so yeah, Terry Tao has this collection of tricks, and one of the tricks is if you're trying to prove something that looks like it's just a strict result, like this number is non-negative, often it helps to try to give yourself some wiggle room. So instead of proving a strict result, you give yourself an epsilon of room, and then try to prove a weaker result that uses that epsilon of wiggle room to make the proof easier. So that sounds very vague, but it will make more sense once we see how to do that in an example. We're going to give ourselves an epsilon of room in this proposition. Okay, so I will ask you again, since my mouth is getting dry from speaking, to read the proposition.
All right, Mike is unmuted. Proposition. Let f of x be a real valued function, and suppose f of x is greater than or equal to 0 for all x. If the limit of f of x as x approaches a equals L, then L is greater than or equal to 0.
Good.
Shall I read the exploration?
Yeah, if you want, sure.
Exploration. Intuitively, we wouldn't expect that a strictly non-negative function could get arbitrarily close to some negative number. How do we make this precise? My idea's here. Your idea's here. I don't even know.
Someone. You probably chose to read the exploration since you hoped that you could interpret it as my ideas instead of yours, since you were the one speaking. But unfortunately, they will be your ideas. Okay. Well,
no.
First, is the idea of what we're trying to show clear? Can you think graphically? What does this mean? You have some function that's always above the x-axis. It's above or hits the x-axis. So the output is always at it's non-negative, so it's positive or 0. And then we're trying to show that if it has a limit, that limit must also be positive or 0. So we're tempted to say this is obvious. You might be tempted to say, well, the outputs of the function are always non-negative. So this limit should also be non-negative. But remember that the limit does not need to be an output of the function. Right? For instance, you could have a function with a hole or something. So there is no relationship between the outputs of the function and the limit values in general. So we have to be a little more careful. But okay, so is that statement of what we're trying to prove, that the value of the limit is non-negative, intuitive to you or clear?
Yes.
Okay. So I'll show one picture, which is a related problem. It's not the same problem, but so here's the idea of giving yourself an epsilon of room. Here's so you can consider two different points, say L and L prime. So in our example, it might be that, say, L prime is 0 or something, because we know the function is always going to be above one of these. Or maybe we should make the top one 0. So the top one we'll think of as 0, and the bottom one we'll think of as the limiting value. So our strategy is going to be a proof by contradiction. So we'll assume that this thing approaches a negative limit, so L less than 0. And then we'll think, well, this is a line that f of x must always be above. If this is 0, then f of x is always above 0. But it gets closer and closer to a negative number. And here's where the epsilon of room is going to come in. So if you're saying x is always above this line, and you assume by way of contradiction that it approaches something down here, a negative number, then you can pick an epsilon small enough. You're giving yourself this epsilon of room between 0 and the negative limit. You pick epsilon small enough so that the bars of L plus epsilon and L minus epsilon around that negative number lie entirely below the axis. So we're going to pick the plus epsilon and minus epsilon so that these bars are entirely negative numbers. And then we use the definition of the limit, which says if x is within distance delta of a, then all of the function values are inside these bars. That's the contradiction, because we pick these bars so that they're all negative numbers. But since the limit exists, we can make the function lie entirely within these bars, except at that point. But if the function lies within bars that are all negative numbers, that contradicts our assumption that the function is always positive or 0, which means it lies above the second one. So again, the big picture is the epsilon of room. You're trying to split these two limits by some epsilon and get non-overlapping bars around them. But, okay, that's very abstract. So thoughts about this? Or perhaps if you have no questions, you can summarize it back to see how well you've got it.
the way I'm understanding this is that, let me think about how to word this. Yeah, the way I'm seeing this, I'm not seeing the part that is. I don't understand why we need an L epsilon. Why did I say L epsilon?
L plus epsilon? Yeah.
L prime. I don't understand why we need an L prime here, because it sounds like we're trying to show that as that epsilon, excuse me, the resulting quote-unquote epsilon bars, that if they're below 0, then it's no longer a, like, I can't think of how to word this.
It's no longer non-negative?
Yeah, it's no longer non-negative.
Yeah, I agree. So if I had the drawing pad, I would have drawn this with not an L and an L prime. I would have just made the first L 0, and I would have made this L with epsilon bars. So there would have been just one. But the tablet's broken, so I just went to Art of Problem Solving and picked the closest picture to the thing I would have drawn. So you should imagine we get rid of the top L and just make this 0, and there's just one L that we're picking epsilon bars around.
So I was getting hooked up on the drawing.
Yeah, but it's reasonable because I picked a kind of suboptimal one, so I apologize. Is it clear now, though, knowing that the drawing is not quite right?
So was my summary at all close?
Yeah, that's exactly right. So we're going to pick epsilon bars, and it's okay to say words like epsilon bars since we're still in the exploration phase, because we have not defined the words epsilon bars. But yes, we're picking epsilon bars so that the epsilon bars around that negative number don't cross the x-axis. They don't go into the positives. So to make that precise, I should ask you, what value, well, there's many possibilities, but give me a value of epsilon we could pick if L is a negative number. What value of epsilon could we pick so that the epsilon bars don't cross the x-axis?
Just pressed Alt because I thought I was using push to talk. I don't believe I'm understanding the question.
Okay, so in the summary, when you told me the strategy, you said the strategy is to pick the epsilon bars so that they contain only negative numbers, right? We're assuming this L prime, which I'm thinking of as L, we're assuming this is a negative number, so it's some distance away from the x equals 0 axis, right? And then you told me, let's pick some epsilon bars so that the epsilon bars contain only negative numbers. So then I asked you to sharpen that statement a little bit. What value of epsilon, how big should we pick the epsilon bars to guarantee that these are only negative numbers? So for instance, we could not pick epsilon equals twice the absolute value of L, for instance. That would not work because, say, if L is minus 1, say L is minus 1. If we pick epsilon to be 2, then the epsilon bars around minus 1 will go from minus 3 up to 1. But we're trying to keep the epsilon bars entirely in the negatives, so we can't pick them that big. And then I'm asking, in general, for some negative L, give me some value of the epsilon bars which would work, that would guarantee that everything within those bars is negative.
I'm failing terribly. I believe that we could, an example of an epsilon that could work is 0.1 times the absolute value of L prime.
Yeah, perfect. So you're saying basically get a 10% tolerance, right? 0.1 times the absolute value, good, of L prime, because then you're guaranteed that inside those bars, you're at most like 90% of the way to L prime away from 0. So you're guaranteed it's still negative. Yeah, that works. Basically any number less than 1 times the absolute value of that L prime, or L, would work. Okay, good. So I think you've basically given all of the key ingredients for how the proof is going to go. It just so happens that I picked, instead of 0.1, I picked 0.5. I said pick half the absolute value, because you know if you're within half, then you're not going to get all the way to 0. But 0.1 also works, and it gives you tighter bounds. Okay, so I'll just show you how to make that precise, so you see a way how these type 2 proofs where you use the limit kind of work. Okay, so to remind ourselves the proposition, where our assumptions are f of x is a real valued function, f is non-negative for all x, and we assume the limit as x approaches a of f of x equals L. So all of that is the assumption. This is everything we have. These are our weapons, the assumptions at our disposal that we can use. The enemy we have to conquer, the conclusion, is that L is non-negative. And as I sort of telegraphed, we're going to use a proof by contradiction. So we suppose by way of contradiction that the limit is negative. So the limit is x goes to a of f of x equals L, but L is less than 0. Then we do almost exactly what you said. We'll choose our epsilon to be absolute value of L over 2, or over 10, whatever. So you choose this to be some fraction. Now we apply the definition of the limit. So just to contrast before, the previous problems, we've all been proving the limit exists, so we needed to pick the delta given an epsilon. Now we're using the limit, so we assume the limit exists, which means we are allowed to just say, because the limit exists, we can cook up a delta. We know it exists, so that we don't have to show that you can cook up a delta. We can just use it. So that's what we do here. Since the limit exists, we can find a delta, so that if x minus a is between 0 and delta, then f of x minus L, absolute value, is less than epsilon. And in particular, the epsilon that we picked, absolute value of L over 2. So it's less than that. This is just the rigorization of the statement that we picked the epsilon bars, so that they don't cross 0. Now here's the kicker, the kind of punchline of the whole thing. So for those values of x, by those values or these values, I mean the values between, the values with the property 0 is less than absolute value of x minus a is less than delta. This must be true. The 3L over 2 is less than f of x is less than L over 2. So how did I get that? That's just unpacking this inequality into two pieces. I took the absolute value inequality and wrote it as a chained inequality. Because if f of x is within distance absolute value L over 2 of L, the smallest it could be is L minus absolute value of L over 2, which is 3L over 2 since L is negative. So that's L minus absolute value of L over 2. The biggest it could be, on the other side, is L plus the absolute value of L over 2. But since L is negative, L plus the absolute value of L over 2 is simply L over 2. So I've converted this inequality into this chain. But now we've upper bounded f by some negative number, because L is negative, so of course L over 2 is negative, just by dividing both sides of this inequality by 2. And if L over 2 is negative, that means f of x is negative. That's the contradiction. So the assumption was that f is always non-negative, and we've just said, well, this value of f of x happens to be negative. So we've contradicted that assumption, which means we've concluded the proof. It must have been true that L was non-negative, because if it weren't, we would get a contradiction. Okay, good. Lots of moving parts again. What parts do you want to go through more slowly?
I think I'm getting this pretty well. I would like to look more into... Actually, no. I think I understand this fine.
Okay. Is this
replicating it would be a bit hard, but I think I could do it.
Okay. Yeah, I think you'll get into the swing when you've written out a couple of these that that you can start seeing the way the arguments will go. I've tried to scaffold the first few of them for you to give you an example to mimic, and then once you've mimicked a few of those, I think you'll be able to write them yourself. I think it's very hard at the beginning to go from the exploration phase to writing out these proofs very carefully, just because it's more abstract than what we've been used to. Is this the only step that I skipped and made a little quickly, is going from here to here? So is it clear why this inequality can be expanded into this one?
That is actually the one I was going to comment on, but I realized that basically the way that I don't even know how to word it right, just taking an absolute value inequality and converting it to a regular inequality.
Yeah,
I'm getting that.
Yeah, that's the first step. So there were two steps. One was converting an absolute value inequality to a regular one. When we do that, the step I skipped would have been L minus absolute value L over 2 is less than f of x is less than L plus absolute value of L over 2. So that's the first step of converting the absolute value inequality into this thing. Then the step I skipped is evaluating the left and right sides, because L minus absolute value of L over 2 is 3L over 2. That's only true because L is negative. So do you understand that if L is negative, then L minus the absolute value of L over 2 is the same as 3L over 2?
Yeah, okay. That makes more sense now. Just talking about how L is negative, so it's just L now. That's cool.
Yeah, I think I was somewhat tricky there, but I think 9.2 will have you actually prove some things with absolute values, so then this will be, I think, more intuitive. But okay, let's do another. Okay, so this is related to remember the squeeze theorem we saw a while ago. I don't know if I still have it open in Crida. Well, you're too laggy, Crida. The squeeze theorem that we saw before involved three functions. So if there's one, well, this isn't going to work very well. That one had f, g, and h, and if one of the functions was between the other two, then the limit had to be between the other two. This one, I'm going to just do part of that. So instead of three functions, there's just two of them, f and g. And we're going to assume f is always bigger or equal to g. So f upper bounds g. Then we assume two limits exist. So this is the second type of problem. We're not proving limits exist, we're using the assumption that limits exist. So the limit as x goes to a of f of x equals f, and the limit as x goes to a of g of x equals g. So all of this is assumption so far. Conclusion, then f is bigger than or equal to g. So this is kind of similar to the last problem. In the last problem, g of x was 0, right? F of x was greater than or equal to 0, and then we showed the limit is greater than or equal to 0. Now we've generalized slightly. G doesn't have to be 0. G can be any other function. But we just want to show that if f is always bigger than g, the limit of f has to be bigger than the limit of g. And I think we can do a similar argument where we do contradiction and then use the epsilon of wiggle room to get a contradiction of the assumption that f is bigger than g. So maybe think about it for a bit, and then if you want, you can tell me how you think the ingredients, what would the steps of that look like? What epsilon would we pick, and how do you think the calculation would go?
I have just been interrupted by my father telling me that I have a few minutes to work on this. You're still there, right?
Yeah, yeah. So you want to leave
Okay.
you want to leave now, or leave in like 5 minutes, or what?
Like 5 to 10 minutes. I need to take care of this lawn before the sun goes down.
Ah, okay. Good.
So, It would seem we. It seems like, as the exploration says, take the contradiction. So we need to prove that. Well, let's see. I don't see how this gets more complicated than breaking these two limits into their parts, but I don't see where to go beyond that.
Yeah, so certainly the first step is to unpack these. So this sentence says that we can make the absolute value of f of x minus f as small as we want, less than epsilon. This one says we can make the absolute value g of x minus g as small as we want. And you said we should proceed by contradiction, so I agree. We're going to assume f is less than g. So the next step is to pick those two epsilons in these two limits to separate f and g. So in this case, the picture from Art of Problem Solving is actually better than it was in the previous one, because now there's two different cases. Replace these L and L prime with f and g. We're going to try to separate f and g by epsilon bars that don't overlap. So if the top one is f and the bottom one is g, what value of epsilon could we pick to keep them separated?
I guess that this could be as simple as taking the difference. The difference of these two. Well, difference of these two. Words.
The two limits, the f and g?
Like 0.1 times the difference of the y4 of each of these points.
Yeah, very good. So we'll take, say, 0.1 or 0.5 in mine, since I always use a half for some reason. So 0.1 times g minus f, because we've assumed f is the smaller one in our contradiction. So you just take, say, half or a tenth of the difference. Good, okay. We have like 2 minutes, so I'll show you the proof. This one's a little longer. But what you just said is the basic idea. So start the same way. Suppose by way of contradiction that the two limits exist, but f is smaller. Then we do exactly what you just said. We choose epsilon to be, say, a half or a tenth of the difference, g minus f. Now the tricky part is now we have to use two different limits. So I label the two deltas we cook up by delta sub f and delta sub g. So we choose delta sub f to make the f difference less than that epsilon, and we choose delta sub g to make the g difference less than that epsilon. And then just as before, we take the minimum, because we want the smaller of whatever of those two that we need. So if you choose delta to be the smaller of those two, then we know f of x is upper bounded by f plus that epsilon. G of x is lower bounded by g minus that epsilon. And here I just do algebra. You can kind of do it in your head. F plus g minus f over 2. Well, f minus f over 2 is f over 2. So this is the same as f plus g over 2. Same thing here, distribute the minus. G minus f over 2. Minus minus on the f is a plus, so that's f over 2 plus g over 2. So the right-hand sides are both f plus g over 2. And combining those inequalities gives us this thing. F is less than this junk, which is less than g. That's the contradiction, because we assumed that f was always bigger than or equal to g, and by separating them with the epsilon bars, we got the contradiction f is less than g. It's probably much too fast, but you probably have to go, so we can discuss this one more later to go through the details if you like.